So, Izzy and who's there, thank you for joining, and James and Patrick, if you're going to watch this later on record. You still owe me, please, Patrick and James, the unit test for Chapter 8. It's all set up on assignments, so that would be great if you guys could get that done, please. Izzy, as I was just saying, very well done. You hardly got anything wrong. So we're going to kick off with Chapter 9, and the first bit. So constant acceleration, all right, so we're just, that's what we're going to be looking at here. So the first bit, 9.1, displacement time graphs. So really that's distance time graphs, just like you've done at GCSE. So we've got time along the bottom and your displacement going up the side. So clearly, if there's no change in displacement, you're not moving, you're stationary. Clearly, if the displacement is just going up at a steady rate over time, you're traveling at a constant velocity, and if your rate of change of displacement is going up, then your velocity is going up all the time, you're accelerating. So pretty straightforward stuff. So you'll see that these examples are very typical to GCSE, so you're just going along for a bit and you're stationary for a bit and then you go back to where you started, type of thing. So a couple of simple examples leading you to exercise 9A. So just quickly rattle through that, please. It's straightforward stuff. As I said, it's not any harder than GCSE. That then leads us on to 9.2. So I would like you to get 9A and 9B done for the next lesson, please. I want to sort of get through this easier stuff quite quickly, so we can spend our time when it just hots up a little bit. So we're now looking at velocity time graphs. So obviously time going along the x-axis, our velocity up the right axis. So clearly, again, if you've just got a line along the x-axis, your velocity is 0, you're stationary. If your velocity is constant, then fine, your speed just isn't changing. So you've got 0, you're not accelerating, it's just constant velocity. And then clearly, if your velocity is going up at a steady rate, then you've got a constant acceleration. Now, with these velocity time graphs, so the slope, the gradient represents the acceleration because it's the rate of change of velocity. This chapter we're just dealing with constant acceleration, so these lines are going to be flat. It's just going to be a straight line. So clearly, to work out the gradient, it's just y step over x step. So you just get a triangle and you do your y step over the x step. So your acceleration for velocity time graphs is your gradient, but the displacement, the area the distance traveled is the area underneath the line. Okay, so this rectangle here on a velocity time graph represents the distance traveled. So you're just obviously going to just multiply base by height. So you will find that they're not difficult, but they're comparatively difficult questions here, where you're going to have velocity time graphs. You're going to be being asked to work out the area under the line. So just so yes, it's a simple enough example here. So we're being here's a velocity time graph. We're being asked for the displacement over the 12 seconds. So we're just working out the area of this shape here. It's obviously a trapezium, so they've just worked it out by averaging the two parallel sides and multiplying by the height and then halving it. So you're averaging the parallel sides. So that length added together with that length divided by 2 to get the average, multiplied by the height. Of course, if you wanted, you could just work out the area of the rectangle, the area of the triangle, and add them together. So easy enough. So the displacement is the area under the graph. The acceleration is the gradient. So this deceleration here, we can work out by working out that gradient. Deceleration, so of course the acceleration will be negative. Example 3, yeah, so a classic sort of question here. So we've got a couple of unknowns here, okay? A couple of unknowns, just following the information that we're given. Because they tell us that the total displacement is 600, we know this area under this graph has got to equal 600. So again, they're using the area of a trapezium. So we've got, so we're going to be averaging our two parallel sides. Obviously, this length here, this parallel side has got a length of 5t. This length here has got a length of 6t plus 40. So we've added together those two parallel sides and halved it to get the average. We've then multiplied it by the distance between the two parallel sides, which is 8, and that equals our 600. So we set that equal to 600. That allows us to work out our unknown t. And that's it. We're then into exercise 9b. So I would like you, please, all of you, to rattle through that. Yeah, there's a few questions there, and that's quite a nice one, question 8. Just checking, I don't think I see you for a little while. I think that was the point. I don't think I see you now until next week. I think that's really why I wanted to set both of them. Yes, so I don't see you again till Monday. So that's really why I wanted to give you a bit to get on with, please. Yes, so for Monday, my plan is that we'll start looking at SUVAT. We'll go from 9.3, my slide 20. So in short, if you could get 9A and 9B done, Izzy, and also James and Patrick, if you pick this up on the recording. I've also set the work on show my homework, so there's no excuses for not realising what's been said. Is that all okay, Izzy?
Yeah, that's fine.
Yeah, okay. Cheers then, Izzy. Take care.
Yeah, that's fine.
Oh, good, James. No, nice to hear.
I think
You're right,
Patrick's
James?
here as well. Yeah, Patrick's
Oh,
here
and
as well.
Patrick. Well, you all three there. Hello, Patrick.
Yes.
How are you?
Yeah, I'm good, thank you.
Good. Oh, it's great. That's super. So, I don't know if you guys picked it up straight from the beginning. So, if you could, when you get an opportunity, please get that unit test done for the previous chapter 8. That would be super. So I've had it from Izzy, but so James and Patrick, if that could be on your to-do list, please. And once you've done that, if you can just get it through to me, I'll get that marked just so we keep up to date.
Okay, that's fine.
Okay, cheers, James.
Thank you.
Patrick. Nice hearing from you guys, and well done, and Izzy. So take care, guys. Bye.
Okay, bye.